Okay, let's press on so we can get out of here before 9024 students turn up and start invading. Getting a freebie sitting up the back and watching the last 10 minutes. No, there's no one there yet. As far as I know, maybe there are. Alright, so the non-unique attribute that we were just looking at, or the indexes involving that, require the data file to be sorted on that attribute. What if it's not? So then we've got a key value 5 over here, a key value 5 over here, a key value 5 up there. That's slightly annoying. The only way you could deal with it would be to have a dense index on that attribute, and you'd have multiple entries for each of those k equals 5 in the index. Of course, the index file, once again, is always going to be sorted on the key value. In this case, the attribute AS. I'm not sure why I suddenly put an S subscript on, but there you go. Yeah, but the issue here is the index is going to be bigger than we want because we've got multiple entries for the same key value. In the previous example, we didn't. We had a pointer to the first instance of that key value, and we knew that all the other tuples with the same key value were going to follow on in the data file straight after that. So, a possibility, and you can see where we're heading with this, is to have a separate index file. And so, at the top level, we've kind of gone back to what we had before. We've got one entry for each key value, but that takes us to another index file which has just tuple IDs. So we're going to have a sequence of tuple IDs here that all of those tuple IDs refer to tuples and have the key value K1. And for key value K2, we've got 3 tuples. Now, it just so happens that all of the key values occur in 3 tuples in this example, but that's not necessarily going to be the case, and K3 like that. So, how do we do a search? Imagine that we're looking for K2. Well, we can look through the index file, we discover this, we go to here, go to the secondary index file, we look at we grab the tuple ID for that tuple, grab the tuple ID for that tuple, and by grabbing the tuple ID, I mean we grab the page number, so we can eventually go back and just read the relevant pages, and we grab the tuple ID for that tuple. How do we know when to stop scanning through here? Well, we simply go until we find the first tuple entry for the next key value. Okay, so these pointers here can bound how far we have to scan through this secondary index file. So what's the cost? The first cost is doing a search in the main index file to find the actual key value. The second cost, well, that depends. It really depends on how many tuples happen to have that key value. If there are 1,000 tuples that have key value K2, then we're going to have to scan a long way through this secondary index file, which is what I'm trying to indicate there. Now, of course, scanning through here, we're not directly, for each of these, we're not going to go directly to the page, we're just going to remember which page is relevant, and once we've scanned through all of these, we're then going to go to the pages that were indicated. Now, we're unlucky here in that, you know, all of the K2 tuples happen to be in different pages, but you know, occasionally they're not. And so what this is talking about is the number of pages that we actually have to read. Remember, I talked about BQ as the number of data pages that contain tuples that satisfy the query. And without knowing what the query is and without knowing stuff about the distribution of values for these keys, you can't really tell what that's going to be. And similarly, you can't really tell how big it is unless you know the order that the tuples are inserted. You know, maybe all of the K2 tuples ended up in this page, in which case all of these blue arrows would be pointing to here, and there'd only be one page that we needed to read. For range queries, why have I got cost range there? I don't know. I thought I'd deleted that, but obviously I didn't. The cost of range queries, once again we find the index entry for the lower bound, and or we find something I didn't say before, we find an index entry that's the maximum value less than the lower bound, less than or equal to the lower bound, and then we can start scanning from that point. So that's how many pages in this file. So log2i is the number of pages that we visit while we're doing our binary search. This is the number of pages in this file that we have to scan to cover the range of key values in the query. And then of course they're going to lead us to a number of index entries, and therefore a number of pages in this file. And then of course the number of data pages that we finally have to look at, which is determined by what's the query and where the tuples ended up in the data file. Okay, a couple of things. These entries are going to be half as big as these, which is nice. So we can fit twice as many of these in our secondary index file. This is, however, going to be relatively small as well, because it's only got one entry for each key value. And that depends, you know, how many distinct values does this particular attribute have. Alright, so what's the cost of doing things that way? It looks like queries are going to be a little bit faster than we get using some of the other indexing schemes, and it's quite likely that something like AQ2 really is only going to be one page that we have to look at. Similarly here, both of these are likely to be one, maybe two, but once again it depends how many occurrences of that key value are in the data. Insertion now requires 3 different files to be updated, and since that file certainly has to be kept in order on the key value, this has to be kept in order on key value as well. So if we add a new entry with K2, we need to add an extra spot there, which means push all those ones further up. Deletion, well, we can use mark style. We can always mark these entries as having been deleted, and we can just skip over them when we're scanning the secondary index file. These ones we can't necessarily delete straight away. We can't mark them straight away. We can only mark them when all of those entries have gone away. If we're doing a lot of deletions, then we might do something like what Postgres does already and have some kind of vacuum function that goes through and compresses the file every so often. So that's one strategy for not having to rearrange the file each time, is just to leave it as a little bit bigger than it needs to be, but then delete it when we can. Alright, so the trick with that previous one was to have 2 levels of index. What we could do is we could just back up to the diagram. Here we've got 1 entry per key value. What we could do, since we know this happens to be in order of key values, is and let's say that's one page in the secondary index file, we could have K1 as pointing there, and let's say we've got K2 and K3 covered as well, so we don't really need those index entries, okay, because we're kind of back to the scenario of a clustering index, so we've got a sorted file that we're indexing into. So if we've got K1 indexing into here, and let's say K5 is the first value in the next page of the secondary index, we'd only need to have K1 and K5 and K whatever. So effectively we could have a sparse index in I1. If any of those index files becomes too large, we can always shrink them by making the level above sparse. And the end goal would nicely be to reduce the top level index to a single page. So when we start our scan, we read this top level page, and looking at the key values in here, we can work out where to go. So let's say our key value is 40. That's between 1 and 53, so it's not going to be in this page here because that only contains key values above 53. So if we're searching for, I should have picked one that actually existed. Let's pick 20, right? So we look in this page, that tells us, alright, so the next page at this level has values up to 20. So this is the page we need to look at. That'll give us a reference to the tuple containing 20, which will be a reference to this page here. So starting to look a little bit like tree traversal, binary search tree. So we start from the root node and we take an appropriate path depending on what range of values that we're dealing with. And it's a pretty short step from that to, may as well skip over that and go straight to B trees. Okay, so basically with B trees, each of those boxes that I showed on this diagram is an entire page. Now, if you think about a search tree and the number of things you can fit in a page, that's going to have a gigantic branching factor, which means that the tree is likely to be very shallow. It might be quite wide, there might be a lot of pages in it, but the critical thing is when we're doing a search, we start from the root and we only have to traverse down maybe 3 levels until we've identified the exact data page that we want, which is okay. So, a couple of things about B trees. The nodes are an entire disk page. The way B tree insertion works, or the way we construct B trees, is that we ensure that each page, or node in the tree if you like, is at least half full, and we update the tree so that it remains balanced. So always, all of the leaf nodes are at the same level, and if you like, the tree grows up and we can eventually add a root to make the tree deeper. The insertion and deletion methods are relatively complicated, so I'm not going to spend time on them here, but they can be implemented efficiently. And the advantages of B trees you can see there, and in particular the trees are shallower and we're not wasting too much space in the nodes, unless you think wasting 1/3 of the space in your data structure is a bad thing. So there's a B tree. So we can see that at the top level, the references out of the B tree go to other B tree pages, and then the references here go to other B tree pages, and finally it's only at the leaf level that we actually have tuple references, tuple IDs. So how deep is the tree likely to be? Well, not that deep because of this giant branching factor. That's the kind of thing we're looking at. So we can have a lot of nodes in a B tree of depth 3, so that means it's extremely wide. But the number of keys that we can deal with, you're unlikely to have a table that has that many different keys in it, unless you're a bank or something like that. So, for most intents and purposes, the maximum depth of a B tree is going to be about 3. And typically it would be smaller than that. And if it's only 1, that's good. So, how do we search in a B tree? How do we insert into a B tree? That wasn't what I wanted to talk about just yet. Alright, so we go to the leaf node. The leaf node contains an array of a sorted array of key values. If you want to sort it, we can do a binary search in that. That'll tell us a branch to take. That branch is a pointer to another B tree node. We go to that. Then we do another search, giving our key value, whereabouts does the key value fall in the range there. We follow another, follow the path to another node, and we keep doing that till we reach a leaf. And then once we've searched in the leaf, we either find the key value that we're looking for, or it's not there. If it's not there, that's good. We know we don't have to read any data. If it is there, then we go and fetch a data page. So this operation here, or scan to find child, is a search within the key values in the B tree page. That's all happening in memory, so that's pretty fast. While it's not a leaf node, that involves reading pages. But given that the depth of the tree is likely to be at most 3, then we're only going to have to read 3 index pages to find everything. So D is the depth, plus 1 is the data page that we have to read. That's for a one-type query. For a range query, then what we have to do is, once we find the lower bound, then we scan through the pages at the bottom level of the B tree. Where's it gone? Oops. That'll do. So let's say we're searching for 15. So we know that we follow that path, we follow that path. We're searching for values between 15 and 30. So we can start from that tuple, or at least we can grab the page relevant to that tuple. And then we can just scan across here. Notice that there are cross links, so that we can go until we find the entry for 30, and then we can stop. Now, of course, these B tree nodes are ridiculously small because I've only got 3 keys in them. As I said, each node is an entire page, so you can obviously fit a lot more than just 3 keys. So that's for a range query. So we have to scan some number of pages at the bottom level of the B tree, and we have to scan some number of pages depending on how the answer tuples are distributed. So, and that's what that is. So D is scanning down from the root to the leaf node, scanning across, and then having determined which pages are interesting, i.e. contain matching tuples, we've got to read those pages. Alright, so let's go back and look at the building. Alright, so if we want to insert these keys into the B tree, if we want to insert 12, well 12 is less than 23, it's less than 13. So we go down here, and there's space in that node, so we can add the key value 12, and we can add a pointer to whatever the tuple is that contains that key value. If we want to add 15, well 15 is less than 23, it's more than 13, so we go down here. Once again, there's room in the B tree node, so we can insert 15 in here, you can imagine we just push 17 along and add a pointer to the node. If we want to add 30, alright, so that's larger than 23, we go down here. It's less than 31, we go down here. Once again, there's space, so we can just stick key value 30 and a pointer to the tuple containing 30. If we want to insert key value 10, and remember that we got 12, so I think that's the next example. Yeah, so that's what we've got now. And this is what happened when we come to insert 10. So, I haven't shown the entire tree, so we got to this point here, we realised that we wanted to insert 10 into this node, the node's full. What do? We split it in half. We got this splitting idea again. We put the smaller keys in one page and we put the larger keys in another page, so we end up with a scenario like that. And the other thing we do is we push one of these values up to the next level. So we end up with 7, 10 and 11 and 12 down here. So once again, these nodes are not full. So the typical scenario is that we come down to a leaf node and it's not full, so we can insert a value into it. Now, of course, if we wanted to insert the value 4, then we have an issue. We got 4 has to go in here, so we'd have to promote a value up to here. That's full, so we'd have to split that node and promote a value up, and that promotion process can go all the way to the top of the tree. And if the root node's full, then we have to add another level to the tree. Right, so what does it cost? It costs to find where we need to insert the node, and then the insertion cost depends on whether we need to split nodes, whether we need to promote nodes, and so on. So in the best case scenario, we simply change one of the leaf nodes and we're done. And that, as I say here, that's going to happen most of the time, given the size of the nodes. In cases where we have to split a node, we clearly got to write the 2 new nodes, and we have to, there's 3 right here, yeah, right. So in one case where we just split and we can promote the tuple up to the parent, then there's going to be a write for each of the low level nodes. I reckon it should be 2W actually, and then a write into the parent node. And that's a read of the parent node, so they're to do with modifying the parent node. If we have to do more than that, then we'll end up with a larger cost. And notice because we've got those cross links, we also potentially have to update other nodes in the tree to fix their pointers. So in the worst case, we have to go all the way from the leaf node and propagate stuff all the way up to the root, and then even worse than that, we have to make a new root. So that would involve that amount of writing. Alright, so Postgres implements a particular style of B trees. Now the way I've described it, if you've got 2 processes that are trying to insert tuples into the table at the same time, and that table has a B tree index on it, then you may have one of the processes might be manipulating this part of the B tree and the other one might be manipulating that part of the B tree. That's fine, but if they're both manipulating this part of the B tree, then we've got to make sure that we don't have any conflict. So one way you can handle that is locking. What Postgres does for B trees, it implements this style of B tree that handles high concurrency. So it tries to minimise the amount of locking that's required. And if you go and look in these files, you can see how well that fits together. And so this is kind of typical of the interface that we have to indexes in Postgres, that you can build a B tree, add a new tuple, start a scan, get a tuple based on a particular scan key, and end a scan. So this scan, begin scan, get next, end scan. We've seen that structure in a few contexts. So same kind of thing here. Inserting into a tuple, and presumably there's also a delete somewhere that I forgot to put on that slide. Alright, so that's all of the ways of improving selection for a single attribute. What happens if we've got several attributes involved in the query? So that's a single attribute, so is that, even though they're different styles, that's potentially a 1 or a PMR, and that's a range query. So one thing about a multi-dimensional query, you're basically specifying more constraints on the tuples that you want, so you're likely to get fewer results. On the other hand, you've got to think about more information, and so potentially it's going to be more costly to deal with multi-dimensional queries, which I'll just call ND for n-dimensional. So there's an example. So partial match retrieval queries where we specify a value for one attribute and specify a value for another attribute. And space queries that I've talked about, remember that I've talked about a tuple space. You can map tuples into a multi-dimensional space, and some kinds of queries will pull out a region of that space. And if these were the only two attributes, then we have a two-dimensional space, and the bounds here would define a rectangle in that two-dimensional space. Alright, so heap files, if all you've got is a heap file, that's dead simple. You just scan through the heap file and you use the matches function to check each tuple whether it matches the constraints. So that's pretty straightforward. So the cost is scanning all the pages, and if you happen to have overflow pages, you'd have to scan them as well. Alright, so if you've got multiple attributes, there's nothing to stop you making an index on each of the attributes. There is something to stop you making a hash-based index on each of the attributes, and obviously until we talk later about multi-attribute hashing, you can only make a hash value on one of the attributes. So that would kind of work. So here, and another thing that this shows is query types. So there are queries that operate on attribute A, queries that operate on attribute B, C, pairs of attributes, and you might even have queries that put constraints on all of the attributes, all three attributes. So that's for a relatively simple tuple type. That's the total number of different query types you can have. If you've got more attributes, then obviously that blows out a lot. Now, if you did an index like this, that would cover all possible query types. So no matter what the user asks, you've got an index that you can use. Unfortunately, having more indices, and also potentially, maybe you don't need these, you can just have an index on each tuple and you can use those two indexes together. But if you want to make sure you can index, you've got an index for every query type, then you're creating a lot of indices, and that's going to have update overheads. Every time you do an insertion, you've got to update all of the indexes, and every time you do a deletion similarly. Okay, so a general view of partial match retrieval queries is something like this. In the case of partial match retrieval, all of these operations are going to be equality, and for a space query, some of them are going to be ranges. If we simply had one index and we happen to have the indexed attribute involved, then we could just use that index, and that would at least save some scanning. If we happen to have more than one index, and we happen to have indexes on a number of the attributes that are used in the query, one thing we could do is we could run the indexing operation and remember that what that produces at the end is a list of pages that we need to go and examine. So we could get a list of pages that were produced from attribute A1, a list of pages that were produced from attribute A2, list of pages that were produced from attribute AN, and then all we need to do is intersect those lists or sets of pages, if you like. And that would give us a list of pages that contain tuples that satisfy all of those constraints that we've put in our where clause. If we've got multiple indexes and we decide, well, it's too expensive to compute all of these matching page sets, and we're just going to use one index, which would be the best one to use? And the best one to use would be the one that produces the fewest pages. And what we'll call that is the one that has the highest selectivity. Okay, so if we've got an index on the primary key, obviously we use that one because there's one page that's going to come out the end. If the primary key isn't involved, and we have a test that happens to be on an attribute that has 1,000 tuples for one of the key values, 1,000 for the second, 1,000 for the third, and we have another index on a different attribute that happens to have 5 values for the one key, 5 values for another key, 5 values for another key. Obviously we're better off choosing the second one, because that's going to probably give us at most 5 separate pages, whereas the other one might give us 1,000 pages. A lot of the time when we're talking about selectivity, we make an assumption that key values are uniformly distributed. That's probably a rubbish assumption, and if you don't want to make that assumption, then you can maintain data in the database, additional data that gives you some insight into the distribution of values. So some databases will actually have histograms of values. So an equality test on a primary key is obvious. You use an index, or use the index on that if you've got one. If you're doing an equality test on a large domain, then the selectivity is going to be quite high. If you've got a range test over a domain, then you're likely to have a lot more matches. So you wouldn't, if you've only got an index on the attribute that's got a range query, then you'd have to use that, and at least it would cut down some of the pages that you need to consider. So this is basically what I think I said before. So we can do an index lookup on the attribute and the constraint on that attribute, and then Oh yeah, and produce a set of page IDs at the end, okay? That's using one attribute. As I said before, if you've got several indexes, you can do this kind of process, get a set of page IDs for each index lookup and then intersect them, and you're done. So that's what we're talking about here. So you can see we do an index lookup like we did in the previous slide. We get a list of tuple IDs and we intersect it with the list of existing tuple IDs. Here I'm dealing with tuple IDs, but I guess I could have at this point converted the tuple IDs to page IDs if I'd wanted to. So the cost of doing that, if there are k queries, k attributes involved in the query, then we've got to do k indexing functions. That gives us a list of pages that we have to go and read, pages that contain tuples that match the query, and then that's how many of them there are. Let's see. Yeah, all right, just a couple of things on this. So, the selectivity of each of these attributes, that clearly has very high selectivity because unique values. Name is reasonably, for a given name, there aren't likely to be too many students who have that name. There's probably going to be more than one, and especially at UNSW. That's true. If we ask a query involving gender, well, we're probably going to have half the queries, half the tuples, whichever value we look for. Birthday will be moderately selective. You know, if we assume a random distribution of birthdays, given a particular birthday, we'd have that. So if the index that we used is this one, 1 in 365.
Actually, it's even better because it's got a year in there as well. So.
Oh yeah, good point. Oh, wow. 1 in the total span of days for students stored in the database. Good point. Uh-oh. They're here. It's kind of like zombie invasion. Right, so using one index, so yeah, you'd obviously, if you had an index on birthday, you'd use it. Clearly we can't use any index that we happen to have on ID because ID is not mentioned there, so we don't know. That's unfortunate because Postgres makes a B-tree index on every primary key. You can't stop it, or you probably can. When you create the table, it makes a B-tree index. I'm sure you could delete the B-tree index if you really didn't want it. Is it worth doing an index lookup on this? My argument would be no, because it's not going to narrow things down a lot. Right, here's another possibility that would help us for partial match retrieval queries. Or, if we structure the indexes right, it might help us with some kinds of range queries, but you've really got to try and preempt the queries that are going to be asked. So, what we have is an index consists of a key value indexed table where each entry for a key value has a bit string where there's 1 bit in the string for each tuple in the table, and there's a 1 if it has a value of red, and a 0 if it doesn't have a value of red. And similarly, here we've got an index that's set up based on relative values of the price. So if I was to ask a query, show me all the red items that are less than $4, the way I can answer that is to take this bit string, take this bit string, and them together, and any 1 bits that were left in the bit string would contain would correspond to tuples that satisfied the query. How would I find those tuples? Well, then I'd need to, all I've really got is the fact that this is tuple 0 matches the query, tuple 1 doesn't, tuple 2 doesn't, tuple 3, tuple 4, tuple 5 or 6 does match the query. So at least I know which tuples in the sequence in the tables, and maybe then, given the tuple number, I can work out what page the tuple's located in. So that would be would certainly be an efficient process, but how long are these bit strings going to be? So we got 100,000 tuples, that's 100,000 bits, which is probably a bit exorbitant. So yeah, that's what I just said about how those things work. So you've got a list of matching tuples here. You work out which bit map is relevant, and you AND it with your current set of matching tuples, and at the end you get a bit string that you then have to go and fetch each of the tuples corresponding to one bit in that bit string. So that's the amount of storage space it's going to cost. Obviously 8 bits and byte. How many bytes are going to be involved? If R is very large, there's going to be a lot of bytes, and maybe the cost of doing the bit operations there is too much. On the other hand, even for something like that, then we can fit a bit map for one of those key values in a single page, which maybe is alright. Yeah, so the cost is obviously we need to read one bit map, so we need to find the bit map. How do we find the bit map, given that we had as an index to the bit map key values? So these key values are obviously not numbers, so we could use some kind of hash table to get to the appropriate bit string. These kind of indexes are only going to work if we happen to ask a particular kind of query. So once again, there's this notion that if you know what your query load is going to be like, what kind of queries are going to be asked, and how often each kind of query is going to be asked. If you're never going to ask a query like this, or very infrequently, it's probably not worth building that index in the first place. If you frequently ask queries where you're interested in a particular colour, then maybe it's worth building that index. Alright, I've exceeded Echo360's capability, which cuts off at 5:55, so let's stop there and I'll talk about more interesting ways of doing n-dimensional queries on Thursday.